Welcome to the session. If you have questions, scan this QR code and do it now, because it will disappear in a second. And I try to cover the questions after the session, and if not, I will cover them when I go out, right? So I will answer the questions. But we have to cover 170 slides, so be prepared. Okay, everybody scanned? That was your chance. And off the Wi-Fi. All right. Let me go back here. Yeah, welcome to the session, Trash Talk. First of all, who is a specialist in garbage collection here? Okay, you can go. This is not an in-deep garbage collection session, right? Because I'm not a garbage collection expert. But I have to share some stuff about garbage collection that might be interesting for you guys. So my name is Gerrit Grunwald, I'm working for Azul, and that should be it. Memory management in the JVM. It's automatic, right? So why care? Any idea? Well, it has an impact on application performance and also on responsiveness and on system requirements. So it's a good idea to have at least a basic understanding about garbage collection. Who really uses, just as a question, who cares about garbage collection here? Who changed the garbage collector according to his application? Okay, and the rest is just using the standard, I guess, which is good, because that means the JVM developers did a good job, right? Okay, and this is in principle how it works. All the stuff that I will show you is the very basic stuff. This is not in deep, right? Just to make that clear. So we have this memory model in the JVM where we have the stack on the left, and this is bound to threads, right? And then we store primitives and references in the stack frame. And this is local access, so that means it's thread safe, right? And then we have the heap where we store all the objects. This is a shared space. So this is not thread safe, and that needs garbage collection. And then we have on the right side, we have the meta space. And to make it short, everything related to classes that is needed by the JVM to load and handle classes is stored in the meta space, okay? We will mainly focus on the heap here, because this is where the garbage collection happens, okay? And the stack frames grow and shrink dynamically, so there's no garbage collection in there. And if we just take a look at this very fancy program here, then we see that we have a record, and then we have some instances of that. And if we now take a look, how would this apply to the JVM memory management, then first of all, we have this thread for this application, and then we have the stack. And we see we have the references for these person objects here, right, on the stack, and for the list. And then if we go to the heap, then we have the actual objects in the heap. And you see these pointers from the references to the actual objects in the heap. And you see the one to the list, and the list points to the objects again, right? And why is that important? Because if I do something like, first of all, these are all reachable now, because if I have them in the stack, I can reach them in the heap by these references. But if I now set P1 to null, that means the reference on the stack is not available anymore, right? Because I set it to null. But it's available on the list object. So you can get still the object by getting it from the list, right? So this is something people not always know, that this works, right? If you have collections and you have objects, references in collections, they're still in your heap because there are still active references here. If I now set the person's list to null, then the reference is gone, right? Then it's more or less garbage, okay? So now I can only reach these 3 objects on the heap, and the rest is just lying around and takes up the space. Okay, so these are now garbage, right? The references and the 2 objects there. Okay, this is just the basic thing, how it works in principle. If we take a look at garbage collection, then first of all, what is it? It's automatic memory management, identifies and reclaims no longer used memory, and ensures efficient memory utilization. It frees users from managing memory manually, which is a hassle. Some C++ programmers here? Yeah, it's nice, isn't it? And we have different phases of this garbage collection process. And if we talk about this one, then we first of all, we have to identify the dead objects, the garbage, right? So this is the so-called tracing phase. And then the next thing is we have to reclaim it. So that means freeing the memory that was taken by the dead objects. And then in the end, we have to compact stuff to make larger amounts of memory available to the application. So we have tracing, freeing, compaction. And we will take a short look into that. So if we start about collectors, and this is not the garbage collectors, this is basic principles of garbage collection. Then there's, for example, the non-moving collector, or mark and sweep. You probably heard about that. Who heard about mark and sweep? Yeah. Who knows how it works? Okay. So I created a little demo that shows you how it works. So we have a mutator, that's the allocator, allocating free memory, right, from the free memory. And then at one point the heap will run out of memory and we have to do something. And you will see that there are objects, the purple ones, that means we have references and at some point we don't use them anymore, so they become dead objects. That's the purple ones here. And if you see numbers in there, that only means, and this will be the same for the other collectors, that they survived the garbage collection. That's what it means. Okay, so we will fill up the heap, then we will stop the world, we will mark all the objects that are live, then we will remove all the dead objects, and then we will continue. Right? That's the idea. So let's start it. Yeah. So we see it's collecting, all good, and you also see objects are dying because not longer used. Oh, that's all fine. Just keep watching. Now, when we reach the end of the heap, something has to happen. Okay, we stop the world, we mark it, remove the rest, continue. And you already see what happens. Right, and now again, fills up, oh, no space, stop, mark, remove, continue. That's how mark and sweep works. And you might already see the problem here. It's defragmentation, right? Or fragmentation, not defragmentation. You see we have a cluttered heap, objects sticking around. It gets harder and harder to allocate memory. And this is a very basic thing where I just say, I only allocate objects with one size. There could be bigger objects, right, which makes it even harder. And so you can imagine the biggest problem is fragmentation with this kind of collector. It starts fast, but the longer it goes, the more problematic it gets to allocate memory. Okay, easy one. Non-moving collector, mark and sweep. If we move to a moving collector, that means you might already get it. It's mark and compact. It's a compacting collector that tries to solve the problem that we saw before. Same thing, but now we start collecting stuff, and before we run out of heap, because we have to keep some space for the compaction, you will see what happens. We mark stuff, remove stuff, and then we compact everything to the left, like defragmentation. Who has know the old Windows stuff, right? This is exactly what happens here. It's like the hard drive defragmentation. So we fill it up, we stop the world, mark, then free, compact, go again. It's way easier to allocate memory here, right? Because we always have a free area in front of us. We can just go. That's the idea. That's pretty good, but as you can imagine, we have to have some headroom, like that could be 20 to 50% of the memory, to make sure to compact means moving stuff around on the heap that we can compact it. So this is a little bit of a drawback, and the compaction also takes some time. Okay, and this is linear with the heap size. So if the heap gets bigger, you can imagine how long it takes to compact afterwards, right? Okay, that's the mark and compact. The next one is the copy collector, mark and copy. And this all leads to one thing in the end, so you will see. And the copy collector looks different. Now we have two spaces. We have the to space and the from space. And we start allocating in the to space, right? So we allocate stuff in the orange area. And when we run out of memory, instead of removing stuff here, we just mark the stuff that is live and copy it to and then we switch the spaces to and from will toggle all the time. If it runs out of memory, we mark the live stuff, copy it to the then to space, and then we can just remove everything in the former to space. You will see. So, again, same procedure, less memory, but now you see we will only mark stuff, copy it over, and you see it will switch to orange on the right side right now, move it, and then we can just remove the whole thing here. And then again on the other side. So we go back and forth all the time, right? That has a big advantage because we don't have to really compact in the same heap. We just don't care about the old area. Everything that's dead, we can just remove it. Because everything that's live, we already copied over to the other area. Okay, so that's the copy collector. Also very basic. And these are in principle the basic principles that we have here. Problem is, if we have long-living objects, you have to copy them all the time, back and forth, right? Because they stay. And the other thing is that we need twice as much memory, because we have to have the same amount for the copy process. Okay, that's the copy collector. Now, because these are the basic collector algorithms, if we combine them to a new thing, this is a so-called generational collector, and this is generational mark and compact, then that looks different. And the idea behind it is the weak generational hypothesis. That means objects die young. This is not only for Java, this is for all languages. Scientists figured out that objects don't really live for a long time. They die very quickly after they have been allocated, most of them. So it's the curve is like this. You probably saw that somewhere, right? And if we have the short-living, medium-living, long-living objects. And if we now tailor the heap according to this principle, it could look like this. For the short-living, for the young generation, we have the Eden space, that's the yellow one here. And then for the medium-living, we have the copy collector, as you remember. And then we have for the long-living objects, this is the so-called to-nerd space. So we have the young generation here on the left side, old generation on the right, and we do different collections here. So we do a minor collection in the young generation, right, because we have to do it more often. And then we do a major collection in the right side, and if we do a full collection, then it means both. We do a minor and major collection. And I also have a little demo for that, and then you get an idea how that works. If it works. It works. So you see Eden, we allocate memory, okay, mark it, copy to the survivor spaces, the so-called ones, and then until they fill up, they will be copied to the other. And in this demo, I used 3 generations before I copy them into the to-nerd space to get rid of the problem with the long-living objects, because we don't want to copy them all the time, right? So we just copy them 3 times, and then if they are older, we just move them. And this is in the JVM, as far as I remember, it's 32 times. And now it's a little bit fast forward, because at the end, and you see there's like a wavefront going through the heap on the right side, because objects die. And then suddenly, when this fills up, we have to do a collection. And then we do a full collection. First of all, the heap on the right side. This is mark and compact. We compact it, and then we copy everything from the survivor spaces into the to-nerd, and then we can start with a clean process again. This is how the basic generational collector works in principle. So I hope you get an idea, because this is the principles that are also used in all the JVM collectors that we have, right? So especially the generational thing. As far as I know, all the collectors except Shenandoah are now generational in the JVM. Okay, one thing we have to keep in mind is if we have the young generation, right, we have objects there, and we have the old generation, the blue area, right, then there might be, and we have the roots, that the roots is the stack frames, right? So we have a minor GC. It means only the young generation. We do a collection there. So that means we have links or references from the roots down to these objects. But you see, we also have some, they go in the old generation, which is fine. But what about these ones? If they go from the old generation, the young one, And now we do a collection in the young one. That means we move stuff around. That means the red reference wouldn't work anymore, right? Because it would point to something that we move to another area. And for this reason, for example here, right? So how do we know what is with this reference? The garbage collector should know that there is a reference. But we only do it on the young generation here. So therefore we have the so-called remembered set. It's a so-called card table where the JVM keeps track of these references and marks them, so that the garbage collector knows, oh wait, before I do the minor collection, there is also a reference from the old generation in the young generation. So I have to keep in mind that I also have to update this red arrow when I move stuff around. And you will hear that quite often, right? Card table or remembered set. Yes, so the GC looks up the card table, and then it finds the references from the old to the young generation. Okay, that's all nice. That was all serial. We stopped the world, easy peasy. What about doing concurrent garbage collection? That's a different story, right? Concurrency is hard. And if we do concurrent marking, then it means when we mark the live objects, at the same time the allocator is allocating new stuff. How do we know, right? So if we have, for example, these are our stack frames, or one stack frame, and we have the objects and the references in the heap, then we start marking live objects. So we start, okay, this one is reachable, nice. Then we mark it as live, then the next one is reachable, also nice. And then suddenly the allocator get the idea, wait, you know what? I just removed this reference and I create a new one. But the collector already passed that. So it means it doesn't know that this reference was removed and that there's a new one now. So what should it do? So it won't be detected by the garbage collection, and because it was really a dead cell before, the garbage collector would remove it. And that would be the worst case. How can we solve that? Well, there's something called barriers, not only in the JVM. The idea is that we have read and write barriers here, and it's some kind of a mechanism that you install in front of objects, right? So that means as soon as you would like to write to a cell, first of all, you have to execute that code. And that code could be whatever, right? And then the write and read barriers means either on each write to the memory cell or on each read, you have to do it. You have to execute the code. Fact is that we have way more read accesses than write accesses. So that means if you use a read barrier, it has to be very efficient, because otherwise it will drag down performance, right? This is something you have to keep in mind. So it's usually people prefer using write barriers instead of read barriers, because they maybe make 30% of the access rate, and the read barriers would be triggered by 70%, so which is really way more. They keep track about these intergenerational references and other stuff, and they're also used to synchronize the collector and the allocator in terms of concurrent collection. Okay. Yes, read barriers are usually more expensive. How it works is, if we have this example, again, we start marking. We find the first one, this is reachable. We mark it as live. We go to the next one, and then we install a write barrier, also on the first one. I just showed here. What happens now, when the allocator decides to remove the reference and create a new one, the code in this case would be, you know what? If you remove a reference, then mark this one that you remove as reachable. And that would lead to the fact that the collector can go on, right? And then in a so-called remarking phase, it will just find the ones that have been marked after he passed that nodes. It's quite complex, right? And I tried to make it as easy as possible. I hope you can follow. And then it can mark it as live, and it won't be removed by the garbage collector. So this is if you use a write barrier, and usually you would install it on each of these cells, right? I just showed it on one to make sure this is really not garbage collected. So this is also called snapshot at the beginning. But like I said, we need a remarking phase. So we mark first everything that was marked in between. We have to go again, do a remarking phase, only the stuff that then was marked as reachable, mark this live, and then continue. Concurrent copying is even more complex. So if we have an object and we have references that point to the object header in this case, and now we copy that, right? So we stop the world in a normal stop the world garbage collector, we stop it, we copy everything over, we update with the forwarding pointer, we update all the references. Once we're done, we continue running the application, everything's fine, okay? If we do that concurrently, looks different, because we would do this, then we start copying, and suddenly, because now we didn't stop the world, also the second header is absolutely available, and that means suddenly both objects are available to these threads, and they will access both objects at the same time. And it's not really nice, right? So that wouldn't work. So we have to do something to stop access to both objects and only make one object available for accessing it in concurrent situations. So the idea here is, this is just one idea. It's a so-called Brooks pointer. There are other ways to do that, but this is the example using a Brooks pointer. What we do, before we copy, we install a forwarding pointer that points directly to the same header, okay? And then we copy the object. And with this one, the other header is not reachable in this case. Now we can copy stuff over, and what happens then is, once we're done, we just move the forwarding pointer to the other header. And then every thread that will access the left one will be passed to the other object. And so the left one won't be accessed anymore. So this is how it works then. And once we're done with updating all the references, we can remove the dead object. This is how a Brooks pointer works in general, right? So this is used if you do concurrent copying objects in memory. And you see, and this is a very simple example, it can get really complex. So just to give you an idea, and maybe if you take some stuff with you from the session, then should be write and read barriers and stuff like a Brooks pointer and things like that. So now, if we take a look at the collectors in the JVM, we start with the serial collector, which is the oldest one. And I try to make it compressed. It's a lot of information here. This is available in all JDKs. This only applies for OpenJDK. OpenJ9 is different, right? Is someone using OpenJ9 here? Yeah, so this different collectors. Some of them work in the same way, but mainly they are different. So this is usually good for single core systems with small heaps, smaller than 4 gigabytes. If you don't have any pause time requirements, be aware that this collector will be chosen by the JVM automatically if you just have one CPU or if you have less than 1.8 gigabytes, as far as I remember. Because then the JVM decides this is not a server-side system. And then you only get, even if you decide to set it to G1, it will take this one. Right? Just be aware, especially if you go into cloud environments where you try to have a very small node with just a little bit of memory, you might end up with this collector, which doesn't mean it's a bad thing, right? But be aware. So it's best suited for single-threaded systems, development environments, or microservices on very small nodes. And you can set it like you see on the lower right. And all the other stuff you find on the left side. It's too much to go through it. Yeah, it's automatically selected on single processor systems, and if the memory is less than 1.8 gigabytes, then you will get this collector automatically. Okay. Next one is parallel. And the idea here, it's even a quite old collector. It's also called the throughput collector. And throughput means it's the relation between time you spent in the application and time you spent in garbage collection. And the difference between this one and the serial one is that instead of having one thread doing the garbage collection, you use all the available threads at the same time. And you can imagine if you stop the world, use all available threads to do garbage collection, the time that you spend in garbage collection can be very small. And you spend a lot of time in the application. That's the reason why this is called the throughput collector. And it's very good for batch processing, for example, scientific computing, data analysis and stuff like that. So it's quite a good collector for some use cases, not for everything. And I have an overview where you see later on the advantages of each of them in one chart, which might help. So it was the default collector between JDK 5 and JDK 7. And then we come to this one, CMS, which is in the meantime deprecated. So that means I have it in the chart. I think it was removed with JDK 14, if I'm right, and already marked as deprecated in JDK 9, I guess. I'm not quite sure. Yeah, response time, that was different. So this is in principle the CMS, concurrent mark and sweep, looks very similar to the one that I showed you with the generational collector, but it was concurrently working. So that means instead of just doing stop the world, it allocated at the same time where we did the collection stuff. This was, I say was, because it's not available in the current JVMs. Oh, by the way, who's using JDK 8? I just talk about production here. Okay, someone below JDK 8, which is good. JDK 11, okay, 17, cool. 21, nice. The Fearless, 22, 23 early access. Yay! Okay, so yeah, like I said, this is a deprecated collector. I won't go into detail because it is, when I saw the latest, there was a poll, and I saw that still many people seems to use it. I can't, who's using CMS here? One, okay. Any reason why you don't choose G1? Use G1. So this was deprecated as of JDK 9. Wow, good remembering. And removed from JDK 14 on. So it's not in the JVM anymore in OpenJDK. So if you try to set it, you will get an exception here. So then we have G1, and this is a different one, right? This is garbage first. That's the name of it, the idea. And it looks different. We saw before we had this specific areas in the memory, right? The Eden space, then we had some survivor spaces, then we had the heap. This one splits the heap into regions. And you see it on the left side. This depends on the available heap size, right? So if you have less than 4 gigabytes for heap, then each of the regions will be 1 megabyte. They can dynamically grow. They can't shrink. So once they grow, they stay at the largest one. And there's an example. If you have an 8 gigabyte heap, you will end up, in this case, with 4 megabyte region size. So the idea is now we start allocating, and we allocate in this region. It's still an Eden region, but it's just small, right? And that gives us some freedom, because when we fill it up, we just take the next one, and so on, and so on, right? And at one point, because there's specific, you see it on the upper right side, there's a specific rate of young generation related to old generation. So at one point we have enough Eden space, Eden up from the heap, and then we have to compare how much garbage is in each of these regions, right? And because objects die young, as we saw. So that means in these two regions, we have the most garbage, the less live objects. So we can just move the stuff from there to another region, to a survivor space, for example, and then remove it, right? So like this. And then we clean up the two Eden spaces. Now we have a survivor space. So then over time, that looks like this. And then again, if we have a survivor space that's filled up, at some point we create inert spaces. So objects get promoted from survivor spaces in the old generation. So the generations are still the same idea, but the heap is split up in these regions. That's the difference here. And then you see we have these humongous regions. Because if you have objects that don't fit into half of one of the regions, we have to give it more space. So in the end, the heap looks like something like this. And that can change all the time. Stuff can move around. This is way more flexible, because you can imagine you don't have to for example, compact the whole heap, because you just have to compact the regions. So the whole garbage collection process is way faster if you use this approach instead of having fixed regions. Right? This is the idea behind region-based garbage collectors. And that was the first one that came with it. Well, this is the default garbage collector since JDK 8, and it still is. So if you don't do anything and you have more than 1.8 gigabytes and more than one CPU, you end up with this garbage collector if you use OpenJDK. And it's a good collector. As we saw, most of you use it, and I think it works quite well, right? So, and you can read it by yourself. I don't read through the stuff. It is, it's a good garbage collector, but it was not good enough, right? So there are other ones. So like I said, it's the default collector from JDK. I thought it was JDK 8 onwards. Then there is this one. Who knows Epsilon? Yeah, because this is quite interesting. This is the non-garbage collector, because it is no garbage collector. So that really means you say, I would like to have 4 gigabyte of heap, and that's what you have. And once it's filled up, you get an out-of-memory exception. So you might want to ask yourself, why? What's the reason? Well, the reason is you can, for example, test your application performance, because then at this point, if you know exactly how much memory you need, no garbage collection is going on when you do your testing. And that means you really get the plain application performance, which is great. The other use case would be very high performance applications where you exactly know I don't need more than 2 gigabytes of RAM, so I can run the whole service in this amount of memory, then you don't have any garbage collection. And that's, of course, if you really need the latest drop-off latency or throughput, then this is the one to go. But be aware, it's hard, because you really need to know how much memory you consume. Okay. This is only available in OpenJDK. There's, as far as I know, there's nothing comparable for OpenJ9, but I might be wrong. Shenandoah, who knows that one? Is someone using it? Okay, so this was invented by Red Hat, and this is also a region-based collector. It's made for very low response times, large heaps, predictable response times needed. So that means if you have a really latency sensitive application and you need to make sure that the response time is always within a certain limit, this is one of the collectors that you could use. Right? It's a quite good one for that. And for this one, it's not available in Oracle JDK. Maybe because it was not invented by Oracle, I don't know. It is part of OpenJDK, so all other OpenJDK builds have it, but the Oracle JDK hasn't it. So just be aware, if you use Oracle JDK, you can't use Shenandoah. It has a bit reduced throughput. And because if you do concurrent garbage collection, this is also one of the pauseless collectors, right? You can think about, you have, let's say, 100 threads. And if you use a parallel GC, that means you have the 100 threads as long as the application works. You just stop the world, then you have the 100 threads to do the garbage collection, and then you have again 100 threads continue working on the application, right? If you use this collector, then you have 100 threads to run the application and do the garbage collection at the same time. This is for all the concurrent garbage collectors. That means the throughput is lower than with the parallel collector, definitely. There is a little drop in performance that you can measure. Okay, and this also uses read barriers and write barriers to get the performance out of it. Then there is this one, ZGC, which will probably be the next default collector in OpenJDK. And it's, again, a region-based collector. And the new version, the generational one, has a young and an old generation. And it's, again, it's very similar to G1, but we don't have really an Eden and Survivor and to nerd, we just have young and old generation here. So we have the young generation, and they age, and when they age enough, they become the old generation. So aging means surviving garbage collection cycles, right? So, and then in the end, the heap looks like this, something like that, right? So it's very similar to the G1 from the arrangement here. How it works is a little bit different, and I will come to that in a minute, because there's one more. This is a very high throughput low response time collector. It's made for large heaps up to 20 terabytes, and you have predictable response times. It doesn't mean it's needed for everything, right? And this should be the main thing here. If you work with your application, the first thing you should do is, if you're fine, you're fine. Don't try all the other stuff just to make, because everybody else does, because Netflix does it, right? Netflix recently came out with the blog post. They switched to ZGC, and they saw a really huge improvement, and they just saw a drop in performance of 3%, right? which is great. But this is the 3%. That's the performance drop that I was talking about when you do concurrent garbage collection, right? You have a drop in performance. It needs more CPU and memory. This is just the way it works. It's very good for highly concurrent applications, for large-scale systems. It's really great. It will become the default garbage collector in the future. The non-generational version is already deprecated, so it will go away. That was, I think, before 22, if I'm right, or maybe 21, I'm not sure. It was only the non-generational was the default, and now the generational will become the default in the JVM. So then there's one more. This is this so-called C4, which is by Azul. It's a little bit older already. It's more than 10 years old. And the reason why I mentioned this one here is that ZGC is more or less a copy of this one. It's exactly the same algorithm in the non-generational. The generation is a little bit different because in ZGC they used write barriers, where in C4 we only use read barriers everywhere. Right? This is the main idea. And this also applies for ZGC. It's best used if you use transparent huge pages, right? Because this is bound to the memory pages of the operating system. And if you have huge pages in Linux, you get larger areas that you can use. It's not like in G1 where we have the region size depending on the heap size. This is depending on the page size of the operating system, also for ZGC. And how it works, and this is the same for ZGC, that's the reason why I put it here. It's if we have the concurrent marking, then how it works, and this is the really big difference to all the other collectors. In the others, it's always we have the collector, we have the allocator, they don't know each other, right? Here it's different. So we have the GC threads, they start marking stuff in the heap. So they reach out, mark it, okay, this is live, all good. And then suddenly the allocator starts allocating stuff at the same time. And now the big difference is that the application thread, the allocator itself, triggers the loaded value barrier. It's a read barrier. And this code says, test and jump. This is one instruction on the CPU level, so it's very fast. And what it does is it tests, is it a reference? Is it reachable? Yes, mark it. The allocator does it. And then it tells the garbage collector, by the way, I marked this object. And that means we don't have a remarking phase that we saw in the other collector, right? Where we had the concurrent marking, we have to mark first, then we have to remark phase, and then we can finally do it. With this one, when the application thread, the allocator also marks stuff and tells the collector, then we only have to mark objects once. You don't have to do it twice. So that's a big advantage here. And so yeah, we don't have to remark stuff again by the garbage collection cycle, which is a pretty big advantage. And the other one is we have something that is called quick release. And I will shortly explain what that is. Because if we have the standard approach on top and the C4 approach on the bottom, we see the loaded value barrier, the read barriers between that. So that means when we start copy things to another area here, then usually you install a forwarding pointer on the object, right? And then you move stuff over. Everything that points to this object will then point to the new one. In ZGC and C4, what we do is, instead of putting the forwarding pointer in the object, we put it in a separate memory area, which is off heap. It's always the same area. That means in this light blue area, there's the forwarding information for this moved object. So, and this, what it does is, every time you access the loaded value barrier, it will look up the forwarding area and then it knows the new location. That means even if we have one left here, and now suddenly the application thread starts to access the same area, the old one, right? It will do the test and jump. It will test, is it a reference? Is it reachable? If not, then take the information from there and update it. And then even the last one will figure out, okay, it's all updated and we can directly release the object. The physical memory will directly be released. Where in the old approach, when you save the forwarding header in the object, in the old object, you have to keep it in memory as long as all the references have been updated. And only if all references have been updated, then you can remove it from the memory. Why is it important? Because if you free up memory as fast as possible, allocation is faster, right? So this is the quick release stuff. Quite complex already. Yeah, this is pretty much the same as for ZGC. Difference is it's only available in Azure Zing JVM. It's only available on Linux. No Windows, no Mac, sorry. The difference here is we don't have the overhead for the performance because we have a different compiler. So instead of having the C2 compiler in the JVM, we have the Falcon compiler, which is our own, which creates faster code, so we can compensate this gap of performance, which is the reason why you have to pay for it. Sorry, that's the way it is. So the question is which one to choose. We have all these different options. In principle, you have 3 criteria, so which is throughput, latency, and resource usage. Well, the bad part is you only get 2 out of 3. So you can't get all 3 of them. So it's your choice. Either you get very high throughput and low resource usage, but then we have a higher latency. Or you say, I would like to have very low latency, very high throughput, then you have more resource usage. So this is how it works, right? And I found this diagram, and that helps you to choose the right collector for your kind of application. On the left side, you see it's increasing the runtime overhead, and it's decreasing the pause times, and vice versa on the other side. So if you would just like to start with whatever, go with G1. It's a good choice. In future, it will be ZGC. But if you have specific needs, you can figure out on your own which collector might be the right one. And then it's worth playing around with it and do some measurements. And here's a little overview, which is a lot of stuff. But I think the slides will be provided so you don't have to read it. You can make a screenshot if you like. But this more or less gives you an overview of what is available, how it works, is it parallel, concurrent, heap size, pause times, and so on and so on. This is really only scratching the surface. This is so much stuff in there, and this is really just to get a basic understanding. But I hope you get an idea, and I have no idea how I'm on time, probably over, I don't know. Does someone know how long the session goes? 170 slides, baby, I'm good. Okay, any questions? Oh, I have to check my app. I just learned this, there is this app. No question. Oh, yeah, there's one question. The collector animation all identified some blocks as dereference before finishing scanning whole memory. Can there be a reference at the end? Well, this is just a demo. This is not a real collector, right? Usually, when we stop the world means the allocator doesn't really allocate anything. So at the moment we stop it, nothing else will be allocated or referenced or dereferenced, then only the collector is working. As soon as we remove the stop and resume, then allocator can allocate again. So this is I hope that answers this. Otherwise, I will be, if you go outside, there's a Fuji podcast booth. I will be there if you have any questions that I can answer. Anything else that I can answer right now? I hope everybody's awake. Oh, there's another one. Okay, let me check. What is GC at Azul Zulu? Yeah, this is the C4 collector. Azul Zulu, sorry, Zulu. OpenJDK, whatever you like. Zulu is a build of OpenJDK. It's the same as SAP Machine, as Tamarin, as Oracle JDK. These are all builds of OpenJDK. So they build on the same source. They add specific features. As long as they pass the TCK, they are more or less the same. That means in Zulu, which is just a build of OpenJDK, we use just every collector that you saw. Only in Zing or Prime, we have only the C4 collector. This is a high-performance JVM, which is mainly for really large applications that need very low response times and high performance. But Zulu is the same as every other build of OpenJDK. So it doesn't matter if you use Corretto, or like I said, SAP Machine, or Alibaba Dragonwell. It's all, if it's built on OpenJDK, you have these collectors available, except Oracle JDK and Shenandoah. This is not available there. But everything else is available and with the same switches. Anything else? No more questions. Then you're good to go. Thanks for attending. I hope it was not too dry.